Okay. So this is going to be really one of the most important concepts of the entire course, just because there's so many places where it can be taken advantage of. So first, some essential definitions. So set of vectors, K vectors is orthogonal if their inner product is 0 whenever I is not equal to j. So the inner product of any two distinct vectors from this set is 0. And orthonormal if their inner product is the Kronecker delta, which, as I mentioned before, is the expression that's equal to 1 if I is equal to j and 0 otherwise. So another way of putting it, orthonormal vectors are also orthogonal, but we can also add that the 2 norm of each vector, which happens to be square root of the inner product itself, is 1. Just a quick example. If I let x be 2, y is 4, 2, 1. When we look at the inner product, dot product, so let's multiply corresponding components and add them up. And sure enough, you get 0. So these vectors are orthogonal, but neither one of these is a unit vector. So these are not orthonormal. So what we can do is normalize. So if I define x tilde to be x divided by its own 2 norm, so 1 minus 3, 2. So if I take the square root of sum of squares, so it's divided by square root of 14. So now that vector is normalized, and I do the same thing for y. So 4, 2, 1 over square root of 21. Again, square root of sum of squares. Then we could say that x tilde, y tilde are orthonormal. So if you take the inner product of any one of them itself, it's 1. And the inner product of x, y of each other is going to be 0, just because all we do is normalize. It's not going to change the orthogonality. Okay. Now, so here we have orthogonality of individual vectors. We can also extend this concept to describe what it means for 2 subspaces to be orthogonal to one another. subspaces, S1, S2, up to Sk, and these are all subspaces of Rm, so vectors of length m. We say that they are mutually orthogonal if any two vectors chosen from distinct subspaces are orthogonal. So if x belongs to Si, y belongs to Sj, I not equal j. Okay. So as an example, I'll let n equal to 3. So I could define S1 to be a set of all vectors of this form. X, first component x, and the other two components are 0. And then I could define S2 to be a set of all vectors of this form that has only a y component and no x or z component. So S1 and S2 are mutually orthogonal. Actually, another way I could have described either one of these spaces using a span, I could say that S2 is a span of E2. E2 is the vector, the second column of identity. So all components are 0 except for the second component, which is 1. And span, normally span of a set of vectors is a set of all linear combinations, but span of a single vector is just all multiples of that vector. So these two are two descriptions of different descriptions of the same space. Okay. Now, so this leads to a concept called orthogonal complement. So if you have a subspace S of Rm, this subspace, S with a perpendicular sign as a superscript, and the way it's read is S perp. And that's called the orthogonal complements of S. And the way I define the orthogonal complement is a set of all vectors. Okay, so I use Y. A set of all vectors in your space such that it is orthogonal to every single vector in S. Now, these spaces are not entirely disjoint. So you could say that, like for instance, any subspace has to have a 0 vector. But the point is, if you have S, you can think of it as dividing up the vector space Rm into two subspaces. You have S and S perp. And every vector in one subspace is orthogonal to every vector in the other subspace. It's like a partition of your vector space into two mutually orthogonal subspaces. Okay. So as an example, of orthogonal complements, so I have two two-dimensional subspace of R3. Okay. Now, I only have 3 dimensions to work with. 2 of them are taken up by S. So I define S to be the span of V1 and V2. So S perp is going to be a set of all vectors that are orthogonal to both of these. Now, who remembers from calculus, if you have 2 vectors in 3-dimensional space, how can you find a vector that's orthogonal to both of them? What operation lets you do that?
Cross product.
Yes, it's cross product. So S perp can be defined as the span. No. Oh yes, it is the span of V1 cross product V2, which in this case is well, in the notes I have 1, 0, minus 1. That would work just as well. You're taking all possible multiples of it. So R3 is partitioned into 2 subspaces that are mutually orthogonal, S and then the orthogonal complement. And dimensions of them have to add up to the dimension of the entire space, which in this case is 3. Okay, so you can check any linear combination of these vectors is going to be orthogonal to this one. Okay. So, because if I let X belong to S and Y belong to S perp, then X has to be a constant times V1 plus a constant times V2. And then Y, being S perp, has to be a multiple of this vector. So I'm going to call this V3. So I get C3, V3. So now if I take their dot product, so X transpose Y, so that's going to be C1, V1 plus C2, V2, transpose C3, V3. And if I work all this out, then I get C1, C3, V1 transpose V3, plus C2, C3, V2 transpose V3. So I boil down to inner products of just one V with another. But both of these are 0. So no matter what the constants are, the inner product is going to be 0. So that verifies that S perp really is your orthogonal complement of S. Is there any questions about orthogonal complement? All right, and I have this in my notes. I said out loud, but I should have it in writing. That give us vector space of dimension n, and S is a subspace of V. That means that the dimension of S plus the dimension of S perp will always equal n. Okay. Now, the orthogonal complement gives us a way to relate certain subspaces that I talked about before. I talked about the null space of a matrix and also the range of a matrix. Because of the range is a span of the columns of a matrix, and then And then a null space is a set of all vectors that you multiply by a matrix to get 0. So to recap, let A be a m by n matrix. The range of A is a set of all vectors y in R m. That can be obtained by multiplying A by a vector in Rn. Okay. Whereas the null space has a set of all vectors x in Rn such that Ax is 0. Okay. Now, let's suppose that I have a vector x that is in the null space of not A, but A transpose. So A transpose x is equal to the 0 vector. And then, if I assume that vector z is equal to, is in the range of A. So that means that z is equal to ay for some y in Rn. Okay. So now I'm going to take a look at z transpose x. Well, z transpose x, so z is equal to ay. And using a property that the transpose of a product is a product of transposes, I get y transpose A transpose x. But x is in the null space of A transpose. So this is a 0 vector. So, what I've just shown is that an arbitrary vector in the null space of A transpose is orthogonal to any arbitrary vector that's in the range of A. So what I've just shown is that the range of A orthogonal complement is the null space of A transpose. And of course, this goes both ways. Like the orthogonal complement of the null space of A is the range of A transpose. Okay. Any questions about how that was shown? Okay. Well, yeah, I think I had Y and Z switched from the notes, but, well, I wanted to do it differently just for fun, so that's what happened. But the essential manipulations are the same. Okay. Now, okay. I'm thinking back to like what you often do in a first year algebra course, where you're, and this is what Dr. Harris happens to be teaching currently in Math 326 is how to find the null space of a matrix. So really what he describes is that you're solving a homogeneous system of linear equations. You're setting ax equal to 0 and trying to solve for x. And then, so in other words, you're computing the null space. So the null space of A is the orthogonal complement of the range of A transpose. So really what you're doing is you're trying to find vectors that are orthogonal to all the columns of A transpose. But that means you're trying to find vectors that are orthogonal to the rows of A. But really, yeah, it doesn't really play to how you actually compute a null space like in a class like 326. But this is numerical linear algebra where we have a computer do all the heavy lifting anyway. Okay. You just have MATLAB do it. Okay. All right.
Can you write the same thing for domain?
Oh, no, domain, okay. Even though range for a, how I've been using it for a matrix is similar to, okay. You think of a matrix, not as an ordinary, just a matrix by itself, but also a linear transformation from like Rn to Rm. Then the range of a matrix is the same as the range in a function sense of that linear transformation. But then the domain of a linear transformation is always like whatever input vector space you have, Rn, it's always the whole space. So now what you could do is you could say that from your domain, you could divide it up into like one part of it that is the null space of a matrix, and part that gets mapped to 0. And then you have everything that is orthogonal to that, which happens to be the range of A transpose. But there aren't any relations like those that specifically applying to the domain of a matrix. Okay. I knew I was forgetting something. Yeah, so Vivian will have you to thank for seeing anything. Okay. All right. Now, so we have a set of vectors x1, x2, up to xm coming from Rm. So it's important to keep in mind the dimension of a space, M, is equal to the number of vectors. So if this set is also orthonormal, we have M vectors. They're linear, because they're orthonormal, they're definitely linearly independent. You can think of orthogonality as like a stronger form of linear independence. Is an orthonormal set. Then we also say that it is an orthonormal basis for Rm. Okay. So it's very convenient in many cases for a given vector space to have an orthonormal basis for it. Orthonormal bases are not unique. There are infinitely many orthonormal bases for any given vector space. All right. Now, so as an example, if I have matrix Q1, that is m rows and r columns. So we assume that all the columns are orthonormal. Okay, so just make that assumption. And if R is less than M, so in other words, it's a tall, thin matrix. So what we can say is, well, before I begin to that part, so because of orthonormal columns, the columns form a basis for a range of Q1. But if we have not taken up a whole space yet, if R is less than M, then this basis that we have for a range of Q1 can be extended to obtain an orthonormal basis for all of Rm. Okay. So any new columns that you could add belong to a range of another subspace, or a range of another matrix Q2, which is the orthogonal complement of a range of Q1. So I can slap them together into one big matrix Q. There's Q1 and Q2. Q is a square matrix, m by m. So here we have r columns, and here we have m minus r columns. And then throughout we have m rows. So all of the columns are orthonormal. Now, what I can say is Q1 transpose Q1 is the identity matrix. And I'm going to put a subscript to indicate the size of the identity matrix. It's R by R. And that's because all R columns of Q1 are orthonormal. So each element of this matrix is an inner product of any two of the columns. So you're going to get 0 for all the entries except along the diagonal, which is each the inner product of each column with itself. Because Q1 transpose Q1 ij is equal to xi transpose xj. So that's why you have that relationship. Okay. And similarly, I can say that Q2 transpose Q2 is the identity matrix, just of a different size, m minus r. Again, because of the orthonormality of the columns. However, if r is strictly less than m, Q1 transpose, the outer product, generally is not the identity. Now, it's going to be an m by m matrix just because of the dimensions of Q1. But it's not going to be an identity because this matrix only has rank R, whatever R is. So if you take an outer product of matrices of rank R, your product is also going to have rank R, whereas the identity has rank M. Okay. On the other hand, let's take a look at Q. Q has orthonormal columns. So this relationship, it applies to Q1 and Q2, also applies to all of Q. And this is the identity of size M by M. Now, here the rules change a little bit, because unlike with Q1, Q is a square matrix. And what I've just said by making this statement here is that Q transpose is equal to Q inverse. Because anytime you're multiplying two square matrices and you get the identity, one is the inverse of the other. So, but inverse works both ways. It's not just a left-hand or right-hand inverse, it's both hands. So I can say that Q transpose is also identity. So when it's square, you can do that. Otherwise you can't. So that's one cautionary tale there. And what we say is Q is an orthogonal matrix. This is one of the dumbest terms I've seen in a while, because here I just told you we call this an orthogonal matrix, but it has orthonormal columns from this relationship and rows from this relationship. So I don't know why we call it an orthogonal matrix, because it's not very descriptive. You think we call it an orthonormal matrix. But no, that's what they call it, so we're stuck with it. Okay. Now, I've assumed throughout this whole discussion that we have, we're dealing with a real matrix. So very quickly, the complex analog to this is that if you have a matrix U times its Hermitian transpose identity, because your inner products, when you do the complex vectors, use a Hermitian transpose instead of a regular transpose. In that case, we don't call it an orthogonal matrix, we say that U is unitary. Now, orthogonal matrices will be a very important tool for us, especially when we talk about least squares problems and also computing eigenvalues. But orthogonal matrices also have a nice geometric interpretation. They can be, often they're rotations, or they can be reflections. And in fact, when we get to eigenvalues, we'll see examples of both. So orthogonal matrices preserve two norm and the Frobenius norm. So what I mean by that is, first, if I have, to take the 2 norm, I should, okay, yeah. If I take the vector 2 norm here of the orthogonal matrix Q and any vector x, Well, that would be the square root of qx transpose qx. But transpose of product of transpose is in reverse order. So we get x transpose q transpose qx. But q transpose q is identity. So that goes away, and what we're left with is just the vector 2 norm of x. So that works out nicely. Okay. And we also have these nice properties that if q and z, actually I'll do it this way. If A is n by n, q is m by m, and z is n by n, q and z are both orthogonal matrices, the appropriate size. Then multiplying on the left by q and on the right by z does not change the Frobenius norm of a matrix, and the same is true of the 2 norm. Okay. So more norm preservation by orthogonal matrices. Okay. Very frequently occurring kind of orthogonal matrix is something in this form, where your diagonal entries are the cosine of some angle, and then your off-diagonal entries are plus or minus the sine of that same angle. What this matrix does, when you multiply it by a vector, so qx rotates x clockwise through the angle theta. Okay. And if I take the inverse, well, the inverse is just the transpose. So that all that would do is move the minus up here, and that would be a counterclockwise rotation by theta. The reason how I don't always remember whether this particular rotation is clockwise or counterclockwise, so the way I convince myself of what it is, if I multiply this by the vector 1, 0, I think, okay, so how's it going to rotate 0? Well, 1, 0. Is it going to... So here's your original x, 1, 0. Is it going to rotate this way so that the y component is positive, or this way so that it's now negative? And when you multiply a matrix by 1, 0, that just takes the first column. Here the second component, the y component, is negative, so I know that is a clockwise rotation. And then, so if I do this, next time I do this, I'll forget again and refresh my memory in the exact same way. Okay, so that's one kind of orthogonal matrix, but that doesn't cover entirely. So I could have a matrix like this, for instance. So what geometric operation would that perform? Like if I multiply this by a vector, so what you're doing is you're negating the y component, and the x component is staying the same. What would that do? What would we call that?
This looks like a reflection.
It's a reflection, yeah. Yeah, so this is a reflection, in this case, across the y-axis. So you can pretty much describe any orthogonal matrix in terms of what combinations of rotations and reflections of various kinds. You can have rotations in any number of dimensions, but you can always decompose them into products of like 2 by 2 rotations. All right. So in other words, you're talking about rigid motions. Okay. See how we're doing on time. All right. Okay, this is going to be interesting. See how far we can get. But Dr. Schroeder doesn't want anything in particular. Okay. Now, in this next section, I get as far as I can with it. This sort of thing generally is not covered in an undergrad linear algebra course, but it's something extremely important in the numerical linear algebra world, and we'll be using it quite often. And it's called the singular value decomposition, or SVD. Okay. So I'll prove its existence and define it in a moment, but as a Stanford graduate, I guess I'm sort of obligated to make a big deal out of the SVD because it was my advisor, Gene Gull, who came up with the first practical algorithm for computing it for a general matrix way back in 1969, the year I was born. And he did a lot of things during his career, but that was the most significant one. So I guess he kind of peaked early. In fact, his license plate was Prof. SVD. And when he turned 60, they threw a big party for him. On his cake, they put the entries of a matrix. And if you were to compute the singular value decomposition of that matrix, I get what are called the singular values and convert them to letters using like ASCII codes, it would spell out "Happy Birthday, Gene." So, yeah. So he and the SVD definitely went together. Okay. Now, I don't think that's the best idea to take the time to prove this, but I just can't resist. Okay. Now, so let's assume A is any m by n real matrix. So there exists some vector x in Rn that's a unit vector, so its 2 norm is equal to 1, such that if I look at the norm of Ax, the 2 norm of Ax, that would be equal to the matrix 2 norm of A. Because, the way I defined it, is the maximum over all vectors of unit 2 norm of a 2 norm of A times x. So there's some x at which this maximum is achieved. Okay. Now, I'm going to let z equal to ax for that magical vector x that does this, and then I'll normalize it to get a new vector y. Okay, so y is a unit vector. So now I can say that a times x is equal to Because the thing is, the norm of this vector is equal to 2 norm of A. So I can say AX is equal to sigma times Y, where sigma is equal to the 2 norm of A. Because AX is equal to Z, Y is just a multiple of Z. And this is the constant that relates them. Okay. And X and Y are both unit vectors. Okay. Now, if we extend X to an orthonormal basis of Rn, and similarly, I'll extend Y to an orthonormal basis of Rm. Then what you get, based on the previous discussion, we get orthogonal matrices. That I'll call U1 has a first column of Y, and then the rest of the columns I'll just refer to as U2. And that is a square matrix in Rm. And then V1 has X as the first column. The rest of the columns are called lumped into V2, and that is an n by n matrix. Okay. So now, we take a look at this product. U1 transpose AV1. Okay. Now, if I write out U1, that's transpose. It's Y transpose U2 transpose A, and then V1 is equal to X V2. So now I can carry out all the multiplication, and what I get is Y transpose AX, Y transpose AV2, U2 transpose AX, and then U2 transpose AV2. Now, the thing is, AX is equal to sigma Y. So I get sigma Y transpose Y. But Y is a unit vector. So Y transpose Y is equal to 1. And then AX is equal to sigma Y, but Y is orthogonal to every column of U2. So this is 0. And then U2 transpose AV2, I'm just going to name that B. We're not really going to do anything more with it. And then here we have some row vector. I'm just going to name that W transpose. Okay. So, all right, so simplifying, we have sigma W transpose 0 and B2. Okay. Now, I want to take a look at the first row. Okay. So I'm going to take the first row, but I'll make it into a column. S is vector sigma is the first element, and W is everything else. Now, one nice property of vector 2 norms is I can say that the 2 norm of S squared is equal to the first component squared plus the sum of squares of all the components of W. So that would be 2 norm of W squared. Okay. Now the other thing is, okay, I'm going to call this matrix A1. Now, if I take A1 times S, so that would be sigma W transpose 0 B, sorry, that should just be B, not B2. And then S is sigma W. If I were to carry out this multiplication, the first component would be sigma squared plus W transpose W. And then there'd be other stuff down below that I don't care about. And this is sigma squared plus 2 norm of W squared. And then other stuff down below. Okay. All right. Now, but the thing is, sigma squared, sigma is a 2 norm of A. So sigma squared is a 2 norm of A squared. Now, this matrix, A1, is an orthogonal transformation of A. Because U1 and B1 are both orthogonal. So, A1 has the same 2 norm as A. Now, this 2 norm is greater than or equal to the 2 norm of A1 times any vector such as S. So we have this upper bound. Now, this vector has, this is a first component. So the 2 norm of this vector, actually all that's squared, the 2 norm of this vector is equal to the sum of squares of all the components. But, so certainly greater than the first component squared. And then, here, the 2 norm of S squared is equal to this, so I can go ahead and fill that in too. So now I can simplify. One of these cancels, so I get sigma squared plus, so I get that. So now I'm saying that sigma squared is greater than or equal to itself plus something that can't possibly be negative. So what can I conclude about W from this? All right, so I'll summarize. Sigma squared is greater than or equal to itself plus a norm of a vector. Now, a norm cannot be negative. Yes. Norm of W must be 0, therefore W itself, by properties of norms, must be 0. So now, my conclusion of all this is U1 transpose AV1 is equal to sigma 0, 0, and then some matrix B. So it has that form. In other words, I have a block diagonal decomposition. So now what I can do is I can now go to work on B and do the same thing. Find a vector that gives me the 2 norm of B and keep whittling away at, so by continuing this process, I get U transpose AV is equal to this matrix sigma that is a diagonal matrix that has these, and also these entries along the diagonal are, they have to be non-negative because each of these sigmas is the 2 norm of some matrix. Okay. Okay. Now, U and V are orthogonal matrices. So, okay, 15 minutes. So now I can finally state the singular value decomposition because since U and V are orthogonal matrices, I can multiply on the left by U, so I could have A V is equal to sigma U, or I can multiply on the right by V transpose. So I could say U transpose A is equal to sigma V transpose. Now, if I just go ahead and do both of these things, I just didn't want to write that until now. I can state the, oh, I shouldn't have erased it. So singular value decomposition of any matrix A size m by n is A is equal to U sigma V transpose. So A is m by n, so is sigma, same size. U is m by m, V is n by n. U and V are orthogonal. Sigma has this structure that the diagonal entries are the only non-zero entries, and these are the singular values. So sigma 1 is greater than or equal to sigma 2, and so forth. It's a non-increasing sequence, and they all have to be non-negative. And then U these are called the left singular vectors. Now, R is a rank of A, and that's the same as the number of non-zero sigmas. In other words, the number of non-zero singular values is always a rank. And so I'm including the rank in the description of the left singular vectors because these first left singular vectors form an orthonormal basis for the range of A. And then the remaining left singular vectors, those describe the null space of A transpose. Because I can take transpose of both sides. A transpose is V sigma U transpose. So the singular values of A are the same as those of a transpose. And then the role of left singular vectors and right singular vectors switch. I don't have as much room as I'd like. Okay. So V has a similar description as U. It's a n by n instead of m by m. So what do you think these vectors, what subspace of interest would those vectors describe, do you think?
Null.
No. Range? Range of what?
No, range of A is U1.
Yeah. Mm-hmm.
Would it not be? Not E?
It's range of a transpose. Because if A is U sigma V transpose, A transpose is equal to V sigma U transpose. So now V plays a role of U for a transpose. And what about these guys?
The null
Null
A.
A.
Yeah, null space of A. Okay. Three. All right, so some relationships of interest among the left and right singular vectors is A times a right singular vector is equal to this corresponding singular value times the corresponding left singular vector. So it's kind of reminiscent of a eigenvalue-eigenvector relationship, but it's not because the two vectors are different. Similarly, a transpose times a left singular vector is equal to a corresponding singular value times the corresponding right singular vector. Okay. Now, we also have what's called the SVD expansion. Of A. So A, we can write A as a sum of R terms, or R as a rank, of sigma I, Ui, Vi transpose. So in fact, you can use this to describe an economy size SVD. A is U1, sigma 1, V1 transpose, where sigma 1 is R by R. It has all of the non-zero singular values. U1 is M by R, and V1 transpose is R by N. And this is useful in data compression because if you can represent your data using a low rank matrix, so R is small, it's a lot cheaper storage-wise than to store the left and right singular vectors in the R singular values than to store every single entry of the M by N matrix. So if R is much smaller than M or N, you can save space that way. Okay. All right, how are we doing now? Okay. Want to mention some other interesting properties of the SVD. Okay. The 2 norm matrix A is equal to sigma 1, which is the largest singular value. and also the Frobenius norm is the square root of sum of squares of all singular values. So I'll just list the largest R singular values, because those are the only ones that are non-zero anyway. So that's how you can see, I gave this relationship before, but the Frobenius norm is always greater than or equal to the 2 norm, and now you see why. Okay. And if I take this sum and I truncate it, so A sub k just takes the first k terms from that sum of the SVD expansion. So this is known as the best rank k approximation of A. So if you want to approximate a matrix by a low rank matrix, again, that's helpful data compression. Maybe you're not compressing a matrix exactly. Like for instance, image. Images tend to be of low rank, even if the images themselves are quite detailed. So you could compress the image and preserve most of the quality of it, and by storing something that's analogous to the singular values and singular vectors, you can again save a lot of space. So the error is approximation. So A minus AK in 2 norm sense. Well, A minus AK is the rest of the SVD expansion. So they start at I equal k plus 1 all the way up to R. Sigma I, Ui, Vi, transpose. But these describe a singular value decomposition of the error. The largest singular value is going to be the first one that's actually included in the sum, sigma k plus 1. And it can be shown that that is the smallest error in a 2 norm sense that you can hope for. Okay. So if a matrix has any 0 singular values, if it's a square matrix, then it is not invertible. Just like if it has a non-zero determinant. Although determinants and singular values really have no connection between them besides that. Okay. Okay, I only have 2 minutes anyway. All right. I think my brain is in too rough a shape to talk about numerical rank, so I'll just pick up that on Thursday. But yeah, so at least we have these essential properties of the SVD, and the very last topic of the semester that I'll cover is the actual algorithm for computing the SVD. But we'll still be making use of it, because at least the SVD function in MATLAB computes it for you. Okay.